So Bikram, are you ready now to take over?
Yes.
Yes. Okay.
Is it okay? My audible also? Hello?
Yeah. So yeah, introduce Bikram Pradhan. Yeah, will report about space debris detection with ILMT. Yeah. So we see your screen. Yeah. Perfect.
Okay, thank you. Hello, everyone. I'm going to talk about space debris studies and its future perspectives with ILMT. I'm also going to talk on behalf of Soumitra, who is from Indian Space Research Organization, and my collaborators are Professor John, Dr. Kuntal, and Dr. Kumar. So I'm going to talk about why we should care about space debris. That will be my introduction. Then what ILMT going to do about it, and what we have thought about the debris studies in the future. So anything that orbits Earth and we cannot control it is space debris. So its size may vary from few millimeter to a few meters. Well, they are very, very dangerous because of their high velocity. For example, if we see over here, is it interrupting? Okay, just put it over here. Okay, if you see here over, okay, so there is a dent over here caused by a millimeter size object. So you can imagine if a satellite is getting collided by a meter size object, then it will be catastrophic. Moreover, the cloud of small size debris erodes the outer skin of the satellite and thereby reduces its lifetime. Then if proper space surveillance is not done, then even a catastrophic collision over, let's suppose, a reconnaissance or spying satellite may trigger a world war. Well, what has been done till now? So this graph is a plot between the size of the debris that can be detected with different instruments and their numbers. So if we concentrate over this range, which are more than 10 centimeter size objects, then optical telescopes are playing a good part in that. Well, when we come less than 10 centimeters, 2.1 centimeters, then these are mostly dominated by radio dishes. And on top of that, the low Earth orbits debris, which moves very, very fast, are also difficult to track with the help of radio. So this particular range is very, very critical. Well, these are the small size debris, which causes the erosion on the satellite outer skin. And I will be talking about most of these areas that ILMT can contribute in space situational awareness. So let's see how ILMT works in detecting space debris. So this is a TDI mode observation. And when a debris passes through the field of view, let's say like this, then we will see a streak on the CCD image. So we used 1.3 meter telescope in the same observing mode as that of ILMT, and we could detect 13 streaks during 11 nights, the 13th one to be the faintest one. And we considered this streak particularly as to be the detection limit of 1.3 meter telescope. And then we propagated this telescope detection limit to 4 meter ILMT using its telescope efficiency and instrument efficiency. And we found that at 1000 kilometer altitude, which is more or less in between the low Earth orbits, can detect space debris almost 10 times smaller than what is possible with 1.3 meter telescope. Now, why I am talking about low Earth orbit? Just to mention that 80% of space debris lies in low Earth orbit. So these are the assumptions while we formulated this graph. I'm not going to talk much about it as of now. Well, the next thing I'm going to see is, well, as of now, we have been talking about the visual limit. What about the streaks which are not detectable by naked eye? So we developed a technique which is called using match filtering. It is very well-known technique. So a faint debris can be considered as a point spread function on our CCD. And if we propagate over the CCD field of view, when the debris moves, it will get propagated. And at the end, we will see streak. Ideally, it looks like this. So match filtering says that if we can correlate the feature with the noisy signal, we can maximize its signal to noise ratio. Now, how do we get the filter? Just project this PSF over 1D plane, and we will see a 1D profile like this. And this can act as a match filter, where when we correlate this feature with this streak, we can we can maximize its signal to noise ratio. So our technique could detect, can detect, in fact, debris 5 times smaller than the detection limit of the 4-meter ILMT. So as I said before, the detection limit of ILMT at 1000 kilometer is around few centimeter, less than 10 centimeter, and 5 times smaller, than we are coming close to this range. So we are easily covering this range. So ILMT can be wonderful instrument for space situational awareness. The next thing is the well, as of now, we have been working on the magnitude estimation of the detected streak using external catalog, because it is to be noted that to find the apparent magnitude, one needs to know how much time an object has spent on the CCD camera. That is the integration time. And unless we know the orbital velocity of the space debris, we cannot find how much time it spent. So we try to find a very innovative technique by manipulating the CCD clocking to find the orbital velocity independent of any other catalog. So the idea is very simple. Let's see this scenario where debris streak is passing from north to south in a TDI mode, where each p seconds the charge is shifted to the neighboring column. Now, instead of just transferring the charges in one direction, what we do is shift the charges to m+1 pixel. You jump m+1 pixels, you integrate there for p seconds, and you jump back m-1 pixel. Then again integrate there for p seconds and do repeat it. So at the end, what we will get is a trajectory which will look something like this, and the continuous streak will be segregated into different small batches. So each batch over here is correlated with its orbital velocity. So if we divide the length of this streak to the total integration time, we can find the orbital velocity of the space debris, which is fantastic. We will see more about the clocking strategy in the next talk by Dr. Kumar. So the next thing is what else we can do with the space debris detection. So when we see a particular debris multiple times, then due to its internal induced spinning, we will encounter multiple cross section of its surface, and we can better constrain the shape of the debris. In fact, the same thing can be done in one single observation, a single streak, if the debris is rapidly spinning. For example, we can see this collage that I showed you before. The sixth debris streak shows variation due to internal spinning, and possibly we can constrain its shape by fitting an ellipsoid to it, which is fantastic. The next thing is we can formulate better statistics on the debris population. This is animation by a European Space Agency, and most of the data points that you see are simulations. They are not the direct observations, but as you know, that ILMT will be somewhere around this latitude 29 plus 29. So, well, we can better formulate or better give real statistics on low Earth orbits as well as middle Earth orbits. Well, we cannot access the geosynchronous orbits yet, but I can show you that in recent developments, there are going to be thousands of satellites. SpaceX 12,000, Amazon around 3,000, OneWeb 48,000. So there are thousands and thousands of satellites that are going to be launched, and we won't be surprised if they occupy inclined geosynchronous orbit. And in that case, ILMT can also become very handy. So I want to summarize what I have told till now. So as I told before, that ILMT can detect space debris within 1 centimeter to 10 centimeter, which poses highest risk to satellite because they are not trackable. Now the automatic detection technique that we developed can detect 5 times smaller debris than what we could have detected visually. Then the proposed CCD observation technique can enable us to find the orbital parameters independent of any other catalog, external catalog. And in real time, in fact, we can update the existing catalog by that. The statistics on the debris population can be improved, of course, by the due course of time, because thanks to the ILMT that's going to run for 5 years. Then, of course, with multiple detection of space debris, the shape model can be improved. Like we can, as of now, we have just implemented spherical shape. We can also include cylindrical shape or a box shape, which can represent a majority of resident space object. So by saying that, I just wanted to show you a picture taken by one of our engineering assistants from Devastal. So this is a passing International Space Station, and this is the star trail. So we can create an analogy between ILMT, ISS, with a cell phone camera, and space debris. With that, I conclude my talk, and I'm open for any questions. Thank you.
Yes, thank you. Thank you very much.